Alrighty there, Physics 30. Let's get into mirrors. Alright, so we're going to do three types of mirrors. We're going to do plane mirrors, concave, and convex mirrors. And there's a lot of rules and math and sort of stuff to go through here. It's going to be a longer lesson, but pay attention. You're probably going to want to meet up with me and or not Google meet up with me and ask some questions and stuff, but just kind of stick with me on this kind of concept. So plane mirrors are the first one. They're super easy. Basically what happens is that you get a mirror, and what we're going to do is we're going to just do some notation here, just an idea of what's going on, is that we're going to have a positive side of the mirror and a negative side of the mirror, right? Anything that's on the positive side of the mirror is considered real, right? Real, and anything that's on the negative side is virtual. So positive is real, and on the negative side of the mirror is virtual. Okay, because we can't really put a piece of paper on the virtual side. It's kind of what we see in the mirror, right? So this is when you go to a mirror, your bathroom's got a plane mirror. It appears as if your image is inside the mirror, like you're behind the mirror, right? Okay, you can't actually put a piece of paper behind the mirror, right? So that image is actual virtual. It's what your brain is telling you that you see. Your brain is telling you that's where the light is coming from, even though technically it's being reflected off that point. Okay, so your brain doesn't really understand that, so you kind of see this reflection idea. All right, we're also going to use a subscript of I and O. Okay, I is the image, and O is the object creating the image. Right? So, for example, in a plane mirror, we're going to have positive objects. These should all be O's. In a positive object, and we're going to get images that are the same size, same orientation, but it's on the virtual side of the mirror. Because what's happening is the light is going into the mirror and then your eye is seeing it. And that's kind of shown here, right? Is your eye will take all of these rays and associate it back to this point. So the rays never actually are on this side, right? They don't end up over here, right? But what they do is, since your eye sees this ray come from here, it assumes that this ray was actually from here. Your brain thinks it came from there, and it sees this ray comes from here, and it sees this ray comes from here. So your eye's picking up a bunch of rays, and so even though the image and the rays are actually even though the object and the rays are on this side of the mirror, you never actually see it over here. Your brain associates over here. Your brain doesn't understand that it's being reflected very well. Right? So it sees it over here. Okay, so that's kind of how it works. We've got a couple things there. Plane mirrors are super simple. You're probably going to get questions on them. They're pretty straightforward. Okay, so what we're going to get here is we're going to look at images. For example, an ambulance, right? If you look at an ambulance head on, you're going to notice that it says ambulance but backwards. The reason it says it backwards is because your vehicle mirror will actually flip that image. You actually get a flipped image in your vehicle mirror, right, when you're looking back. And so you actually know that. Okay, you actually know that. Your brain knows that. Okay, watch this little video. It's kind of cool. It's talking about curved mirrors. All right. And you can kind of get this idea where a curved mirror can do a lot of cool things, where you get an image appears and objects and all sorts of cool stuff. So this is a little interesting piece here. This little bit here is that perfectly parabolic mirrors or perfectly curved mirrors, or if you were to actually create a circular object, like creating a circular object naturally or man-made is very difficult. When you actually create one, you can cause kind of this to get perfect. You're going to want it to be exact. And so for the Hubble Space Telescope, they made an error of grinding the glass 2 micrometers, which caused, instead of it being 70% of the light focused, it was only 15%, right? And so very small errors kind of propagate when you're talking about mirrors, because if things don't bend the right way or curve the right way, you're going to get some issues. Right now, of course, your everyday mirror on your vehicle or in a store doesn't care about 2 micrometers, right? It can have a few more errors, but the idea is that you create a perfectly circular object and then cut the edge off, and that would give you a perfect convex or concave mirror. Okay, convex means it's coming out towards you. Concave means you're looking into the cave. All right, so just keep that in mind. So convex is if you're looking on the outside where it's vexing or flexing, right? And concave is when you're looking into the image, into the cave. All right. Okay, so let's talk about how images work. So kind of just I ignore this here. All right, just ignore this. We'll come back to that probably in the next lesson. All right. Okay, and so what we have here is we have this idea of this side here is a concave mirror. All right, and what you notice is that all the rays are reflected back towards this focal point. All the rays are reflected back towards the focal point, right? Okay, on a convex mirror, okay, the reason it's called diverging is because it makes the light rays. So all these rays coming in are then reflected outwards, right? So any ray that comes in to a convex comes in and is reflected out, right? Comes in is reflected out. And so what you get though is that if you actually backtrack these images, you'll get a focal point, right? And so there's kind of this idea that you don't get really a lot. So we're going to actually look at different characteristics, okay? We can have images can be produced. So images can be larger, smaller, the same height, right? So I could have, if my original object is like this, right? My original object is like this, I can get an image that's larger, smaller, or at the same height, right? So images have the option to either be larger, right? So I have an image like this, smaller, image like this, or the same height, right? So I can get all those images. They can also be upright or inverted. So the images can also be upright or inverted, which means that the image can also be inverted, right? So it could be down here. Could be down here, right? And this is depending on what kind of mirror and all that stuff, right? It also can be real or virtual. So not only can they also be here, they can also be over here somehow, right? In the real world, right? So if our mirror is here, either concave or convex, we'll get into which one's which. We can have these are virtual image, and we can have real images. We have all the same options. So there's really like 12 or 13, 12, I guess not 13, 12 options that we can kind of get based on this. But you kind of get these all deals. So we have to have real or virtual. Okay, upright or inverted. Okay, upright meaning it's the same orientation, inverted meaning it's the opposite orientation, and larger, smaller, or same height. Okay, so that's kind of the idea. Again, check this video out. It's pretty cool. It shows what a real image looks like. All right, so we're gonna start with convex mirrors. So this is where we're looking from the outside to where it's flexing out. Okay, and what you're gonna notice is when you look at a convex mirror, you're gonna have what's called the focal point, which is it's a virtual focal point. It's on the opposite side, and the center of curvature. Okay, the center of curvature marked with C, and so that's where the C is kind of where it's this point right here. Okay, C is this point right here. It's where if you were to finish the circle off, it would be the center. All right, and then F, and you'll see the slide down below. F is always halfway in between. Use a black mark. So F is always halfway in between. So F is half the distance. All right, so we'll mark this with C and this with F, okay? And what we're gonna do is we're gonna do what's called ray diagrams. All right, ray diagrams means we're basically going to draw this in order to help us figure out where the image is located, what size they are, and if they're oriented, upright, or virtual. Okay. So you can memorize that the curvature is equal to 2 times the focal length. There's a focal length that's half the curvature. Either way, you guys can do that as well. Okay. So convex mirrors have 4 rules, but we're gonna just star on 2 of them. Okay, the green rule and the red rule here. All right. So the green rule tells us a ray parallel to the principal axis is reflected as if it came from the focal point. Okay, so look at the green one there. Right, let me just zoom in on this. Yeah, let me just zoom in on this here. Okay, we're focusing on green. All right, and so what it says is that a ray that comes in parallel, so this is parallel, right? It's parallel to this, parallel to the axis, is reflected as if it came from the focal point. So you actually draw a line, you basically draw it straight in, then draw a line from the focal point, and then keep that focal point going, right? And that's how you would draw that one, all right? Okay, and then the next one is a ray, why are these colors all messed up? Sorry, this is yellow, but it should actually be red, right? For number 2, a ray along the radius is reflected upon itself. So a ray that actually matches going towards the curvature, all right, will actually just reflect back along itself, okay? A ray that's directed towards a focal point will reflect parallel, and a ray that's directed to the vertex will just bounce off the same angle. And what you notice is that we have all of these rays are actually going away from each other, right? They're not converging. But on the opposite side of the image, if we backtrack those images, or those rays, we actually get them all meeting at one point. So all the rays came from the tip of the pencil, and when they all meet, it'll show the tip of the pencil. Okay, and I'm going to draw these out. So number one, okay, I'm going to try and use blue and yellow as my rays as best I can, and I'll use red as my images. All right, so a ray parallel to the principal axis is reflected as if it came from the focal point. So what you do is you draw it going in, okay? You draw a line going in, and then what you do is you take basically a line from the focal point and you meet it and then keep going. All right, the reason that this is solid is because that's what the ray is actually doing. The ray is actually coming in and then reflecting out, right? But we do a dotted line because that ray is backtracked towards the focal point, okay? A ray along the radius, okay? So a ray along the radius, and when it says along the radius, you can also think that this is towards the C. A ray towards C. Okay, a ray towards C is reflected back upon itself. So the ray is going to go in towards C and then back out. And what you can do is actually just draw a line all the way to C, but leave the side on the virtual side, the negative side, dotted. Okay, all right. So then we have the third rule, which is a ray directed towards the focal point is reflected parallel to the principal axis. So if I have a ray that goes towards the focal point, so this is our focal point here. Lost you. There we go. This is our focal point here, right? And so what it's going to do is the rays towards the focal point, it actually gets reflected parallel. So just those two rules kind of go together. A parallel ray reflects if it came from the focal point, and a ray towards the focal point reflects parallel. Kind of always does the opposite. All right, and a ray that's incident on the vertex. See, this is the vertex is where the line and the mirror meet. Okay, a ray that's incident on the vertex will reflect at the same angle. So this angle and this angle equal each other. Okay, so that's kind of it. We're going to draw these diagrams. Now, don't panic. Okay, you really only need 2 rays to solve these problems, and the rays that we use are rules 1 and 4. Okay, we're going to use those. All right, and there's formulas as well. But it's going to take us a minute to get there. Okay. What's important is that wherever the lines of reflection intersect, you're going to find your image. All right, so that's good. Well, you're just looking for where 2 lines intersect. So we only need 2 lines. Wherever they intersect, that's going to be your image. Okay. Also, you may extend your lines back into the mirror in order to find the point of intersection. Right. So we saw that here, right? With the previous question, is we had another ray like this, and then it showed the image, right? So we extended it into the mirror, right? Extended it into the mirror, and that showed us our image being there, okay? All right, so one thing to note, and this is kind of a little important, is that when you draw your picture, you're not expected to be perfect, okay? You use a ruler where you can, all right, but you're just not going to be perfect. And your size may be off through the curvature that you draw your mirror with, and it's mostly use your picture to help determine the orientation and location of the image. All right, so the math is going to tell us how much the height actually changes properly, but you're going to use your mirror and the math to kind of support each other, right? So your picture and the math support each other, right? And they both prove the same thing. So it's kind of important that you understand that, okay? All right, so we're going to practice this, all right? And I've already done a couple. Okay, so use a ray diagram to draw the image produced by the mirror, state the characteristics of the image, and approximate measurements. So we're going to do the measurements, right? The measurements we're going to do later. Okay, we actually learn the math equations in a few minutes here. So what we get here is I drew my first ray. Okay, so I'll just draw this. See how much that is. Okay, that ray right there. All right, so I drew the ray coming in and then going out. All right, and how I knew which angle it went out at is because rule 1 tells us if it's parallel, it'll reflect as if it came from the focal. So I took a line from the focal and just extended it. Okay, again, I used dots on this side. All right, then I've got a second ray that goes towards the vertex will reflect as if on the same angle, right? And so this is this one. This is rule 4. Rule 4 is this one, okay? So that's rule 4. And I did the same thing. I extended back. So if I look at these 2 rays, and I'll just kind of highlight what I'm talking about here with some yellow. This ray and this ray, are they ever going to meet with the directions they're going? The answer is no. Since they're never going to meet, we have to extend them back into the page. So we extend them back. And as we extend them back, we can just go as far as we need to. We extend that one that way, and we extend this one this way, right? It doesn't matter how far we go, but what we notice is they intersect right here. And so what we're going to get is the image is right here. And so we have a virtual image because it's on the opposite side. It's on the negative side. The rays don't actually meet there, right? Our brain would just tell us they are. It's smaller and it's right size up. Okay, instead of right size side up, we're going to try to say upright. Okay. Going to say upright. Okay, inverted or upright are the two words we're going to use. All right. So that's kind of the general gist of a convex mirror. All right. So convex mirrors are are the types of mirrors used in stores, side view mirrors of vehicles, and they always, okay, this is important, they always produce a smaller virtual and upright image, right? So it's why your mirror says objects may appear smaller than they are, right, in your vehicle. So the kind of is, it always does the same thing. It always is going to create a smaller virtual upright. Okay. Yeah, and that's really it. All right. Now we get into concave mirrors. Concave mirrors are a little bit more complex because they can have all sorts of different images and orientations and stuff like that. Okay. So what you should notice here is that we have a focal point that's actually in front of the mirror, right? And so our object or whatever we're using is going to be on the same side of the mirror as the center of the curvature and the focal point. Okay, it's the exact same side of the mirror. All right, so you get into concave mirrors and we have a ray parallel to the principal axis is reflected through the focal point, and a ray incident on the vertex reflects at the equal angle of the axis. Okay, and basically what it is that the rules are the exact same, but we just kind of do in the same way. Okay, one that's sent kind of as if it was going through the center of curvature would also do that as well. Okay, so it's kind of the same rules. Take a second to read through there, but again, rules 1 and 4, what matters the most. All right, so what I've got here is use ray diagram to show the image produced by the mirror, state the characteristics of the image, and approximate measurements. Okay, we're going to just get the measurements, all right? And so what I've got here is I did rule 1 and rule 4. So rule 1 tells me that I'm going to go in parallel. And when I do that, it's going to go through the focal point, and I just keep extending it, right? And then I'm going to have rule 4, which is when I go to the vertex, which is here, I'm going to go out at the same angle. Now, approximate, right? But what you notice is we're going to get an image that's called inverted, larger, or real, okay? And what you see here is that this is the same picture down here. It's just a little bit better drawn, right? This is me using my pen, okay? And so we get an image that's inverted, right? It's upside down, larger, and real. Okay, it's real because if I put a piece of paper here, I would actually see that image on there, right? I actually see that image. Okay, so now what we're going to do here is so that the object right now is between the center of curvature and the focal length. If I move the object so it's closer than the focal length, we're going to get this. Okay, we're going to get this idea. So same thing. We have one go in and parallel, and it's going to come out through the focal point. And then we're going to have another one we go towards the vertex and go down. So now if I look at both of these rays, this ray and this ray, the blue ray and the yellow ray, they're never going to meet. And since they're never going to meet, I'm going to instead backtrack them into the mirror, right? Backtrack them into the mirror. And what I get is that I get an image on the virtual side of the mirror. So I get a larger, upright, and virtual image. Okay, now you're going to get confused. You got to double check. But remember your rules. Take your time. It will all work out. All right? It'll all work out. Now, with convex mirrors, they were always smaller, virtual, and upright. With concave mirrors, we have different options already, right? We have inverted, larger, and real, and we have upright, virtual, and larger, right? So it's not always larger, but it can be, okay? So you can memorize these. These are the diagrams. Okay, so these 2 pages are just diagrams that can help you. You can memorize these different things, and it'll give you different options, okay? Or you can just use our calculations, and that's probably going to be easier memorizing is just using our calculations. All right, okay. So positive and negative, it's for real quote unquote values, and negative is for virtual values. Okay. Um, we're gonna if the focal length on a concave is positive, right, and the focal length on a convex is negative because it's opposite side. All right. So whenever you're drawing a mirror, basically you'll just have to kind of get used to the concept that if the mirror is like this, right, this side is positive and this side is negative. If the mirror is like this side is still positive and this side is negative. So whatever side your object is on, right, whatever side your object's on, is going to be the positive side. Okay? So we're going to keep in mind a few things here. So we get our first equation is this. All right, 1 over the focal length is equal to 1 over the distance of the object plus 1 over the distance of the image. All right, so DO is always positive because regardless of what mirror or anything we have to do, it's going to always be positive, okay? The distance of the object is always positive. Focal length, if it's a concave mirror, right, it's a concave mirror, the focal length is on the same side, so it'll be positive. If it's negative, it's on a convex mirror. For DI, it's real and virtual. Okay, so DI, if it's on the same side, it's going to be real, so it's positive as well, or if it's on the opposite side, it's going to be virtual. All right, one thing also to note is that they don't have to be in meters. Okay, this is one of those equations where whatever units you put in are the units you're going to get coming out. Okay, and that's just something to get used to. All right, but you're generally going to do meters, or if you want to put centimeters in, centimeters comes out. Put millimeters in, millimeters come out, right? And so you don't have to do the conversions for this equation, which is nice. Okay, it's on your formula sheet right there. And then the second equation for mirrors, all right, try and keep track of what's going on here. Second equation for mirrors is this one here, okay, where M is basically the magnification of the object. If it gets larger or smaller, by how much, okay? And it's based on the height of the object and the height of the image. All right, and you'll notice this negative is here. Okay, keep track of that negative because it's going to give you different things. Don't just ignore it. That negative has to be there because we know that if DI is positive or if DI is negative, right, matters. DO is always positive. We know DO is always positive. Okay, HI and HO can be positive or negative. HO is generally going to be positive. It makes sense. Unless, of course, it starts upside down, which would be weird. But then upright is negative, positive, negative, right? So the image can be upright or inverted, right? Okay, and if the image is, and for magnification, if the image is upright, it's going to stay positive. If the image is inverted, it's going to become negative. If it's greater than 1, it's going to make it larger. If it's less than 1, it's going to make it smaller, right? So we're going to have basically these two equations. Now, this has two equal signs, which means we're basically going to deal with just this part, right? We just know that this represents M. Okay, M is sort of unitless, but again, we come to the idea that whatever units we put in are the units we're going to get out. Remember, though, that if I measure this in centimeters, then all of these also have to be in centimeters, right? So you can't put meters into for DO and centimeters in for the image. It's not going to work. They have to all be the same units, but the units just have to be consistent. Okay, so we have this equation here, so the top there, so you have those two equations are kind of what you're dealing with mostly here. Okay, this is a very powerful form that can tell us a lot of things, so we don't have to memorize every situation, right? So if the image is virtual, DI is negative, all right? If the image is real, DI is positive, all right? Okay, if the image is closer than the object to the mirror, DI is going to be greater than DO, or less than DO. And if the image is farther away from the mirror than the object, DI is less than DO, okay? So this helps a lot with kind of what's going on. Okay, so here's sign convention for mirrors. This summarizes all of the little signs, positive and negative, when to use them, okay? You're going to want to basically reference this quite a bit when you're doing these questions, all right? You may want to take a picture of this, right, on your phone so that you don't have to come back and forth to your notes and stuff like that, and just kind of have this idea for mirrors. All right, so we're going to do some class examples. Why not, right? Okay, so I'm just going to do the top part here where I drew it so we don't have to worry about the math. So a 1.5 centimeter tall object is located 10 centimeters in front of a concave mirror with a radius of curvature of 8 centimeters. So the CO... Oh, I made a mistake here. Okay, we're going to say the Yeah, we're going to say that the focal length is 8 centimeters because then it still works, but okay. We're going to say that F in there, put F equals 8 centimeters because otherwise I have to erase everything and it's going to take too long. Okay, so we're going to say F equals 8 centimeters. All right, I guess I can just cross, yeah. Okay, so we're going to say F equals 8 centimeters, not the radius of curvature, because that means C would be 8 and F would be 4, okay? So what we're going to do is we're going to draw this first. All right, so the object is here, this is our F, all right, object is here, this is our focal length, okay? This is at 10, this is at 8, and you don't have to be exact. You can see how my measurements aren't perfect, okay? What we're going to get here is we're going to get an image that comes, a ray that comes in and goes through the focal point, and then a ray that goes and comes through here. And what we're going to get is kind of an image somewhere over here. Now, it doesn't have to be exact, right? We're going to get some kind of image over here. But what that tells me is I should have a larger, farther away, and inverted image. All right, it's also real. Okay, and so what I can do is I can then use that in the math. And so what I did, I started with math. Height of the object originally is 1.5 centimeters. The distance of the object is 10 centimeters, and the focal length is 8 centimeters. All right, and so what I'm going to do is I have DO and F, and since I have DO and F, I can find DI. All right, can find DI from this, and so I'm going to use those to find DI. Now, mathematically, you do 1/8 minus 1/10, and then do 1 divided by that number, and you'll get 40. All right, so DI is 40. Now that I have DI and DO, I can then end one of these and come to this equation here. All right, so remember how that negative is important? I put that negative 40 there, and what's this going to give me when I do this mathematical cross multiply and divide? No big deal there, as I'm going to get HI equals -6, right? So if I look at what I said originally I said it should be larger. Well, is the height larger? Yes, 6 is larger than the image, than 1.5. Is it farther away? Well, the answer is yes. It's at 40, and the original image was only at 10. Okay, is it inverted? Yes, because the height is now negative. Okay, and is it real? Yes, because the DI is positive. Okay, so all those things that I get from my original kind of help me out there. All right, so the diagram and the math are going to support each other in getting these solutions. Okay, so here is this class example again. An object is located 30 centimeters from a mirror. So all it gives me is that DO is 30, right? That's this. So an object located 30 centimeters from a mirror. So DO is 30, all right? Then it says the image is formed upright. So it's going to be positive. We know the image is positive, okay? And it is 1/3 the size of the object. So the image is 1/3 the size of the object, right? Okay, image is 1/3 the size of the object. So image is 1/3 the size of the object, okay? And so what I'm going to do here is I'm going to look at what I have. I kind of have HI and HO, sort of, and I have DI. Basically what I know is that I have my M, right, in this case. If you think about what was your magnification, well, my magnification is 1/3, right? You could use that, or you could do what I mathematically proved that here. And so what I do here is I start with my equation for my formula sheet. I'm going to put in 30 here. And what I'm going to do is I'm going to take HI and replace it with 1/3 HO. Okay, 1/3 HO. Now I can do this. These HOs cancel out. These two HOs cancel out and I get 1/3 equals this. And so my DI is -10. So I'm going to get a virtual image. All right, so virtual image is what I get. But now that I've got DI, I can then go and do this equation because I've got DO and I've got DI. All right, so I'm bringing this up here. And again, you can see multiple step problems mean that we have more chance for mistakes. We got to avoid mistakes as best we can. Now I can do this equation. I'm going to get the focal length is equal to -15. All right, so -15. And that means I have a negative focal length. As soon as I have a negative focal length, I reference that black chart we had there, and it tells me that it is a convex mirror, and I can draw it quickly just looking like that. All right, so there's that question. Take your time, pause the video, and make sure you get this all written down. Okay, All right, the next question here is mathematically prove that if an object is located at the focal point of a concave mirror, that there will be no image. Okay, so if the object is located at the focal point, DO and F are going to equal each other, right? DO and F equal each other. So what I did here is start with the original equation, and then I wrote replaced DO with F. And so what you notice is that I have 1 over F equals 1 over F plus something. Well, in order for that to be true, then that plus something must be 0. So since it must be 0, DI can't exist, right? How do I make, mathematically, how do I make 1 over DI equals 0, right? Well, that would mean that DI would have to equal 0, which can't happen because we can't divide by 0. So it just doesn't exist, right? So if you put an object at the focal length of a concave mirror, you just get no image at all. It just doesn't exist, okay? You can do this with gray diagrams, and it kind of does something interesting as well. Alrighty, so that's kind of that. All right, so look at this. If an object's distance is extremely large, approaching infinity, 1 over di becomes 0. Based on the mirror equation, where will the image form in relation to the focal length of the mirror? So what we're going to do is we're going to basically say that 1 over d0 1 over do becomes 0. So we start with our equation. 1 over f equals 1 over do plus 1 over di. And what we're going to say is this essentially goes to 0. To 0, because we're going to get 1 divided by an increasingly larger number. What that tells me is that 1 over f should equal 1 over di. So eventually, so the image why can't I spell image? Yeah, is at f. Okay, the image will be at f, so that's for part A. If I get farther and farther away, eventually the image will be at f or near f. Okay. All right, so now for part B, so we're going to do mathematical, things like that. For a plane flat mirror, right, the focal point approaches 0. So as the mirror, so a very curved mirror has a focal point farther away, and as it gets closer, the focal point approaches 0. So if I think about this, right, it basically tells me that f goes to 0. And so I'm going to use the same equation, 1 over f equals 1 over do plus 1 over di. And if this goes to 0, right, then essentially, I shouldn't say it goes to 0, this whole thing, 1 over f goes to 0. So this will become 0, 1 over do plus 1 over di, which means that 1 over di equals 1 over do when I rearrange it, right? And so kind of di is going to equal do, which we saw from our plane mirrors, is that when I draw an image, right, if I have a mirror and I draw an image, right, the image is going to basically be the exact same distance and the exact same height and the same distance away, right? And that's that pencil. Okay, so that's for a plane flat mirror. All right, there's a lot in here, you guys. Yeah, good luck. And let me know if you have any questions.